So in the previous video, we went over the geometrical intuition for what the derivative is, and we learned that in order to describe a gradient of a non-linear function, right, we cannot just have one real number describe the gradient. We actually need a function, and the function would be a function would take in a value x, and it will output the value of the gradient at that point x, and the value of the gradient corresponds to is geometrically calculated by taking the point on the graph and drawing a tangent line to it and calculating the gradient of that tangent line. And so now we're going to talk about more algebraic calculations for how to calculate the gradient. So in particular, if I have the function y of x equals to x squared, right? I'm going to show in this video, I'm going to show how we can derive that the derivative, right? Y prime meaning the derivative of y, right, of x equals to 2x. So in this video, my goal is to show you how to reach this step. Yeah, okay, before I talk about that, you see over here that I use some other forms of notation, right? D over dx, f, and df over dx. They all mean the same thing. So perhaps I want to spend a bit of time first on alternative notations, right? We usually denote differentiation by this d over dx. Note that the d and d on the numerator and denominator, they do not correspond to symbolic variables. You cannot just cancel them out, right? This is not the same as 1 over x, right? That's not true. D over dx is a symbol to represent the derivative, right? And what this d over dx does is that if I put a function, if I have a function, I can use d over dx to act on the function to give me the derivative of the function, right? The gradient of the function. And sometimes we shorten the following d over dx to just write it as dy over dx, right? But do note that dy and dx, they're not fractions, right? This is just a symbolic shorthand for this, right? In fact, this is the more original notation, right? Y prime is just a shorthand for it as well. So I'm going to show you how to derive that the derivative of x squared is 2x. And don't worry, we're not going to do this for every single function we meet along the way. We are just going to do this for y equals to x squared. And in future, right, we're actually going to have just a bunch of derivative rules, right? Rules for differentiation. And usually when you calculate the derivative of a function, you just apply these rules. Yeah. So, but I'm going to go through the derivation for how to obtain the derivative of y equals to x squared just for educational purposes. So if the derivative of a function is defined to be the following. So what it looks like is that if I have a function f of x, and I want to calculate the derivative at this point, right? Let's say this point x. Then to calculate the derivative at this point, I need to calculate the gradient of the tangent line. However, how do you obtain the tangent line systematically? To obtain the tangent line systematically, I'm gonna have a, let's say I'm gonna have a value h, right? Such that this is location x plus h, and this point will be x plus h, f of x plus h, right? This describes the coordinate of this second point. This first point is just going to be f of x. Right? The y coordinate is just going to be f of x. So I'm going to first, before I draw a tangent line, right, I'm going to first calculate the gradient of the line passing through these 2 points. Of course, the line passing through these 2 points is not going to be tangent, but the trick is that later on I'm going to take the limit as h approaches 0, right? This limit is something studied in analysis, is something studied in math called real analysis, but we won't need to know too much of the details if we're just doing physics. So to calculate the gradient of this, right, we can see that the gradient is just f of x plus h minus f of x over x plus h minus x, but that's just h, right? And so that's what we see on the expression over here. If we then in this case, the function we are interested in exploring is f of x equals to x squared. So if we expand it out, right, f of x plus h is x plus h squared, f of x is x squared, and we expand it out, right, this is just a binomial thing, then you see that the x squared cancels nicely, and what we're left with is this expression. But this expression, if we factor out h, right, we can cancel the h as well, and then what we're left with is just 2x plus h. And then if we take the limit as h approaches 0, we see that what's left over is just 2x. So that's how we obtain that the derivative of x squared is 2x. There's something I want to know over here, which is that if we had taken the limit over here, if we had taken the limit at this point, then we realize that the numerator as h approaches 0 is just 0, and the denominator as h approaches 0 is also 0. And this is what we call indeterminate in math. And usually when this happens in limits, we need to do L'Hopital's rule. But the key idea over here is just that we see that even though the numerator and denominator both approaches 0, they actually factorize nicely, right, into h, 2x plus h over h. And if we take the limit as h approaches 0 of h over h, it may seem like it's 0 over 0, and then we don't know what's the answer, right? But in reality, right, h over h, no matter what value h is, right, h over h is always going to be 1. So if we're taking the limit of this constant number as some variable approaches 0, this is just 1. So that's kind of the procedure we're doing here, right? And that's the trick we're performing when we take derivatives. So this was how to derive the derivative of x squared, and it's a very common procedure you see in a lot of textbooks. But for most of differentiation that we're going to perform in physics, right, and math, we're just going to follow a set of rules, and it's just about applying these rules to break down a complicated derivative into its constituent parts. And in the next video, we're going to go through these rules.